So this video is on nonlinear data and exponential modeling. We're going to start with nonlinear data. So using logs, we can represent data that is usually nonlinear in a linear format. So this might not make much sense on its own, so it's a lot easier if I just show you. So there are two examples that you need to be aware of. The first example is when y is equal to ax to the power of n. So this is just a polynomial and this is non-linear. Remember, non-linear means it's not a straight line. If it's linear, it's just a straight line like y is equal to mx plus c. And this graph will be a curve. It will be a quadratic if n is equal to 2 and a cubic if n is equal to 3. The point being, it's going to be a curve. It doesn't really matter what type. So for y is equal to ax to the power of n, if we take logs of both sides, which we talked about in the last video of doing, this is going to be log y is equal to log of ax to the power of n. We've just taken logs of both sides. Let's keep this as log y, and let's separate this into log a plus log of x to the power of n. We can do this, remember, about how the laws of logarithm works. If we plus two logs together, they times together, like this. And then let's move this n down as the coefficient. So it's going to be log y is equal to, I'm going to move this to the front here, is equal to n log x plus log of a. And this is a linear graph because this here is the y. This here, I'm going to put an equals here. This here is the gradient. This here is the x. And this here is the c, the y-intercept. This is a graph that is y is equal to mx plus c. So if we plot this log y of n log x plus log a in its y is equal to mx plus c format, with the y-axis being log y and the x-axis being log x, we get a straight line with the gradient being equal to n, which is this number here, and the y-intercept being equal to log a, whereas a is this number here, so it's the log of that number. So this is the exact same data, literally the exact same data, except here we've got a curve because we've plotted y against x, but here we've got a straight line because we plotted log y against log x. When you kind of get further along into maths, especially science, this is something that comes up quite a lot. Not necessarily just using y and x as the y-axis and x-axis, but using stuff like log y and log x, stuff like that. And this is now a straight line. So I know this is kind of a new concept, but this is something, again, which comes up quite a bit as you go further along in maths. But why is this actually useful? Because with this graph here, it's quite hard in order to tell what the values of a and n are. You know, it's quite hard. We need a lot of points in order to kind of do it. But with this graph here, we can easily find the values of a and n because we can easily find the gradient of a straight line. We talked about this in chapter 5 about finding gradients of straight lines, and this will be equal to this value here, n, and we can easily find the y-intercept. This is log of a, so it's the log of this number here. And then when we get these values of n and log a, we can convert back to this equation here in order to get a value for this equation here, because we can figure out the a and the n values from this straight line here. That is what's useful about this. We can, from this graph here, get this equation here and the information for it. So here's an example of an exam question. Sorry, this really big exam question. I've had to go into the kind of new spec because this is something that wasn't on the old spec. But here's an example of a question like this. So for part A, it kind of talks about this kind of like modeling kind of thing of like where it's from. It would be based on real data. And then we have this equation here, and we need to convert it to this equation here. And we do this by logging both sides, as we talked about before. So this is n is equal to at to the power of b, and then we log both sides. So this is going to be log of n is equal to log of at to the power of b. We're going to separate these two, so it's going to be log of n is equal to, and then we can separate these two by doing log a plus log of t to the power of b, and then we can bring the b down as the coefficient to make log of n is equal to, I'm going to put this first, is equal to b log t plus log of a. And this is of the form here, where the m here is the b and the c here is the log a. So for part B, we need to estimate the number of microbes, which is n in this model, present in the culture 3 days after the start of the experiment. And as it's t days after the start of the experiment, therefore t is going to be equal to 3. So what we actually need to do is we need to find the equation for this line and then sub in t in order to get the value for n. So we need to find the equation for this line, and we can do this because we're given this graph here. We can find m and we can find c. We can find kind of the actual values of them. So c is the y-intercept, and there's a lot of perspective. They give you a lot of error, there's a lot of like a big answer range you can give because there's a lot of error you can give. I've got it as about 1.85. That's what I've got the y-intercept at. And then the gradient is going to be equal to, and then basically we need to find 2 points on the line and then find the gradient using, remember the equation of the gradient is equal to m is equal to y2 minus y1 over x2 minus x1, where we have 2 points. And the 2 points I'm going to use is the actual y-intercept, which is 0, 1.85. And I'm going to use this point all the way up here, which is, as I can see it, 1.2 and 4.55. So the gradient is going to be y2, which is 4.55, minus y1, which is 1.85, over the x2, which is 1.2, minus x1, which is 0. And if you put this into a calculator, this is equal to 9 over 4. So we know the gradient is 9 over 4, and we know the y-intercept is 1.85. So therefore, the equation of this line here is log of n is equal to 9 over 4 log t plus 1.85. And now what we can do is sub in the value of 3 in order to get out this value of n. So it's going to be log n is equal to 9 over 4 log 3, and then it's plus 1.85. And if you put this into a calculator, this is equal to 2.923 and then a bunch of numbers. But we don't want to find log n, we need to find the number of microbes, so we actually need to find n. So log n is equal to 2.923, so therefore n is equal to 10 to the power of 2.923 and then a bunch of numbers. And if you put this into your calculator, I get at the value of 838. Again, they give a wide answer range. I think they give it between 800 and plus or minus 150, so this lies within it. They give a massive answer range, but this is one of the answers that you can give, and here's the final answer. So for part C, we need to show why it's unreliable to use this model to predict when the number of microbes is going to be 1 million. So this means that n is equal to 1 million. So therefore, if we convert to this graph, log of n is going to be equal to log of 1 million, which is equal to 6. So we need to show why it's not good, why this model does not work to predict when log n is equal to 6. And the reason is because, see these are the values these are the real data, these are the values that are actually plotted, and these are the only values that are plotted. And log n is equal to 6, you can see that this only goes up to 5, well it actually only goes up to 4.5, but the graph itself only goes up to 5. So 6 is somewhere up here, and you can see that the values that they determined from their experiments didn't go this far. So therefore, they're doing something called extrapolating. They're extrapolating the graph. What that basically means is that they're trying to predict a value, log n is equal to 6, when their values do not represent kind of a line of best fit within this value. If it was anywhere between 4.5 and 0, because the values kind of show a strong correlation here and kind of a line like this, you could definitely use this model to predict this. But because log 6 lies outside here, the line doesn't go this far, therefore it would be unreliable to predict it. Learn this word extrapolating, it's really useful. It's kind of to show that you're going outside how far the model can go. So for part D, you get a lot of these questions for 1 mark. So they want you to interpret the value of the constant A with reference to the model. So basically what they're asking is, for this model, what does A actually mean in terms of this situation here? What does it actually mean? And the best way to always think about this and to figure it out is you basically need to think about, when does n equal A? When does this happen? Because when that happens is what A actually means in terms of the context of the model, is when n is actually equal to A. And n will equal A when this part here is equal to 1, because it will be A times 1, and that is when t is equal to 1. And remember, t is t days after the start of the experiment, so therefore n equals A when it's 1 day after the start of the experiment. So therefore, A is, you could say n, but it's more accurate to say the number of microbes, because again we want with reference to the model. A is the number of microbes one day after the start of the experiment. It's only one mark, but please just try and think about when n is equal to this constant, and then what does that mean? The second example you could be asked is, y is equal to ab to the power of x. This is an exponential and it looks something like this, and this is non-linear and we want to make it linear. So we're going to do the same thing as before. We're going to log both sides. So this is going to be log y, and this is going to be equal to log of ab to the power of x. And then log y is equal to, I'm going to separate these again, so it's going to be log a plus log of b to the power of x, and then we can put this x at the front here, and I'm going to put it at the front, so it's going to be log y is equal to, I'm going to put this here, so it's going to be x log b. As you'll see in a sec y, I'm actually going to write this as log b, and then I'm going to put the x here, and then plus log a. And this is in the form y is equal to mx plus c. This is the y, this is the m, this is the x, and this is the c. So it's y is equal to mx plus c. And for this example, if you plot log y against x, so this time the x-axis remains as x, you get a straight line with the gradient being equal to log b and the y-intercept being equal to log a. So again, this is really, really useful because we've converted this to this by just changing what we're plotting. Here we're doing log y against x, and here we're doing y against x. And what we can do from this is, using the y-intercept and the gradient, what we can do is find log of a, log b, and then we can find a and b for this equation here. It's really, really useful. So just remember that when it's of the form ax to the power of n, like a polynomial as we did before, it's log y against log x. But when it's ab to the power of x, it's log y just against x. So here's another example of a question on this specific example of an exponential. Again, I've had to use the new spec because the old spec didn't ask questions on this. So for part A, we need to write down an equation for L, which is this line here. And we're told that it meets the vertical axis at 5 here. So therefore C, the y-intercept is equal to 5. Then it has a gradient of 1 over 200. So M is equal to 1 over 200. So therefore, because T and log P are the X and Y axes respectively, therefore the equation of L is going to be log P, because that's what Y is, so log P is equal to M, which is 1 over 200, and then the X is the T part, so it's T, and then plus C, which is plus 5. So for part B, we need to find the values of A and B. And A and B are in this equation here. P is equal to AB to the power of t. So what we need to do is we need to convert this to this format. Now remember, as we talked about before, the way we converted this to this format is by taking logs of both sides. So in order to get from here to here, we do the opposite. We make 10 the base of both sides. So this is going to become 10 the base of log p is equal to, and base 10 of 200 under 1 t plus 5. Let's simplify this. So remember that 10 to the power of log base 10p, if these two are the same, then this is just going to be equal to p, and this is equal to 10 1 under 200 t, and because this is plussed in the power, we can therefore write this as times 10 to the power of 5, because remember that when you times powers, they add together, so therefore we can separate these and write them as this. We can simplify this further. 10 to the power of 5 is 100,000, so this is going to be 100,000, and this is the A part, and then the B part is this 10 to the power of 1 over 200 t. Now we need this b part to the power of t, so we need b to the power of t, and at the moment we've got 10 to the power of 1 over 200 t, so we can simplify this, because what we can do is we can separate this and to the power of t by doing the 10 to the power of 1 over 200, and then this to the power of t, because remember that when you do these two actually times together when you do 1 over 200 and then to the power of t, and therefore p is equal to 100,000, and then it's to the power of t, and this here is going to be b, and if you put this into a calculator, this is equal to 1.0116 to the power of t. So this is the final equation. P is equal to ab to the power of t. P is equal to ab to the power of t. So a is equal to 100,000 and b is equal to 1.0116. So for part C, this is another one of these questions we talked about before. We need to reference to the models what the constants A and what the constants B mean. So let's start with A. So remember A is the 100,000 here, and we need to interpret what this means. And again, what we say is, when does P equal A? And this will equal A when t is equal to 0, because then this whole thing will equal to 1, it will cancel out. So when t is equal to 0, and remember that t is the number of years since the population was first recorded. So therefore A is the population when first recorded. So for the second part, we need to interpret what the value of the constant b is. Remember, b is this part here. So let's consider the same thing again. When is p equal to b? And quite annoyingly, p is never actually equal to b, because we have this factor at the front here, which complicates it, because it will always make it bigger than b. So it will never actually be equal to b. What b actually is here is when t is equal to 0, it's 100,000, and when it's equal to 1, it goes up by this, and when it's equal to 2, it goes up by another one of this, and when it's equal to 3, it goes up by another one of this. What b actually is, b is the factor by which the population goes up by each year. The mark schemes states it as the proportional increase of population each year. I've worded it as this because I think this is a bit more easy to understand and to word. But basically, B is for each single year, 1, 2, 3, 4, 5. It always goes up by this factor. So for part DI, we need to find the population that is predicted by the model when t is equal to 100. And this is really easy. We just sub in the value when t is equal to 100. So it's going to be when p is equal to 100,000 of 1.0116 and t is 100. And if you put that into a calculator, it gives out a value of 316 but it says it wants the answer to the nearest 100,000, and to the nearest 100,000 it's going to be rounded down to 300,000. And then for part 2, we need to find the number of years that it will take to reach the population of 200,000. So therefore we equal p to 200,000. So it's going to be 200,000 is equal to 100,000, 1.0116 to the power of t. Divide both sides by 100,000 to get 2 is equal to 1.0116 to the power of t, and then I'm going to take a log of 1.0116 of both sides, so it's going to be log of 1.0116 of 2 is equal to, and then if we take this log on this side, this would just be equal to t. So t is equal to the log of 1.0116 of 2, which if you put into a calculator is equal to 60.2. So t is equal to 60.2. So it takes 60.2 years for the population to reach 200,000. So for part A, this is kind of the question which we talked about before, where we need to kind of think of a flaw in the model and talk in kind of what scenario would it not work. And there's a couple of things, they're very lenient with these because there's kind of loads of reasons you can come up with. A couple of them are given on the mark scheme. It doesn't talk about the fact of like something like a war or a disease could happen that could impact the population. The other problem with this model is that it kind of predicts that no matter how big T gets, the population will just kind of go on forever. It will kind of just go unlimited growth, which of course is not realistic in terms of how a population will actually grow. It will kind of stop at some point. So these are problems with the model. Just kind of try and think of something in a scenario in which the model would not be able to predict and it wouldn't be able to work. So I'm just going to go through some quick exponential modelling questions. We already talked a bit about this in the first video on exponentials, on how exponential modelling is really good and when it applies. And now I think we can go through some more exam questions because we know about logarithms, which come up a lot in these questions. So here's an example question where we're given this formula for the value of a car, and we're told the value of the car is 17,500 when new and 13,500 2 years later. And we're told that k and a are positive constants in the formula, and the first question is we need to find the value of a. Well, this is really easy because we know the value of the car when it's new, so it's 17,500, and this is equal to 16,000 e to the power of minus k, and then the t, because it's new, is going to be equal to 0 because t is the age of the car in years, plus a. Remember that anything to the power of 0 is just 1, so therefore this is just 17,500 is equal to 16,000 plus a. So therefore a is just equal to 1,500. So for part B, we need to show that k is equal to the natural log of 2 over root 3. And to do this, we're going to use this information here, that it is 13,500 2 years later. So this is when t is equal to 2. So v is 13,500, and this is equal to 16,000 e to the power of minus 2k, because t is equal to 2, plus a, which we figured out as 1,500. First of all, I'm going to divide everything by 100, because we can do that, because you see we have these two zeros on the end of every single one. So it can be 135 is equal to 160 e to the power of minus 2k plus 15. Minus 15 from both sides to get 120 is equal to 160 e to the power of minus 2k. Divide both sides by 160 to get 120 over 160, which can be simplified to 3 over 4, and that's equal to e to the power of minus 2k. And then we can take natural logs of both sides. It's going to be the natural log of 3 over 4 is equal to the natural log of e to the power of minus 2k, which is just going to be equal to minus 2k. And then divide both sides by minus 2 to get minus a half of the natural log of 3 over 4 is equal to k. And it wants us to show that k is equal to the natural log of 2 over root 3. So what we probably want to do, because there's no coefficient at the front, is to bring this half into the natural log. So it's going to become the minus half, sorry, the natural log of 3 over 4 to the power of minus a half, and this is going to be equal to, so first of all the minus flips the fraction, so it's going to be the natural log of 4 over 3 to the half. And remember that a half, the power square roots it, so it's going to be the natural log of the square root of 4 over 3, and this is going to be equal to the natural log, the square root of 4 is 2, and then it's just going to be root 3, and this is equal to k, and this is what's required. The natural log of 2 over root 3 is equal to k. So for part C, we need to find the age of the car when the value of the car is 6,000. So V is 6,000, so it's going to be 6,000 is equal to 16,000 e to the power of, I'm just going to leave it as minus kt for now because that's quite a complicated expression. We'll simplify that in a sec. Plus a, which is 1500, divided by 100 again because we can do that. So it's 60 is equal to 160 e to the power of minus kt plus 15, and then minus 15 from both sides to get 45 is equal to 160 e to the power of minus kt, and divide everything by 160 to get 9 over 32 is equal to e to the power of minus kt. Now let's focus on this minus kt for a sec. Minus kt is equal to minus t and then times k, so it's the natural log of 2 over root 3. Because this is a coefficient, the minus t, we can bring this to the power, so this is going to be equal to the natural log of 2 over root 3 to the power of minus t, and we can bring the minus in here to flip this fraction around, so this is equal to the natural log of root 3 over 2 to the power of t. So this is what this is equal to, so therefore this is equal to 32 under 9 of e to the power of the natural log of root 3 over 2 to the power of t. We simplified this, and remember what we said, that when the base is the same as this number here, so this is the case here because it's e to the power of the natural log, this is just equal to this. So this is just equal to 9 over 32 is equal to root 3 over 2 to the power of t. And now what we can just do is find logs in order to find t. So I'm just going to do the log of, and I'm going to do this base here, so the base is going to be root 3 over 2, and then I'm going to do of 9 over 32, and this is going to be equal to t. And if you put this into your calculator with base root 3 over 2 and of 9 over 32, it gives that a value of 8.82. So that's the final answer. It wants it to 2 decimal places. That's the 2 decimal places. So here's another question on exponential modelling. I included this question because I actually thought it was quite interesting about how there's kind of 2 different variables, where d is the dose given in milligrams, and then t is the time in hours after the antibiotic has been given. So we kind of have 2 different variables, and we're told that a first dose of 15 milligrams is given, and we need to find the amount of antibiotic, which is x, in the bloodstream 4 hours after the dose is given. We need to give it to 3 decimal places. So this is going to be x is equal to d, so remember this is the dose in milligrams, and we're told this is 15, so it's 15 e to the power of minus 0.2 t, and we're told that t is the time in hours after the antibiotic has been given, and we're told it's 4 hours after the dose is given, so this is 4, and if you put this into a calculator, this is equal to 3 decimal places, sorry, 6.740. So for part B, we're told that there's a second dose of also 15 milligrams that is given 5 hours after the first dose, and we need to show that the total amount in the bloodstream 2 hours after the second dose is this number to 3 decimal places. So there's a lot going on here. So first of all, the second dose is given 5 hours after the first dose, and we need to find the total amount 2 hours after the second dose. So therefore, the first dose was 7 hours ago, because it's 5 plus 2. And then the second dose is just 2 hours. And then we need the total amount, so this is kind of the combination of both doses, and we need to figure them out individually. So let's focus on the first dose though. So X is equal to, so again it was 15 milligrams, so it's 15 e to the power of minus 0.2, and now it's 7 hours, so it's to the power of 7. And then X for the second dose is going to be equal to, so again it's 15, it's the second dose as well, e to the power of minus 0.2, and then it's 2 hours. So the total amount of antibiotic is these two things added together. 15 e to the power of minus 0.2, 7 plus 15 e to the power of minus 0.22. And if you put this into a calculator to 3 decimal places, it gives out the value of 13.754. So for part C, we're told that at time t hours after the second dose is given, the total amount of antibiotic in the bloodstream is 7.5 milligrams. And we need to show that t is equal to this expression here, and we need to find the value of A and B. So what we're going to have to do is we're going to have to create an equation considering both the first dose and the second dose. And the way that we can do this, so first of all, this is going to be equal to 7.5. And then let's consider the doses individually. So first of all, let's consider the second dose. So using this equation, this is equal to, again, D was equal to 15. So it's 15 e to the power of minus 0.2, and then t, we're told, is t hours after the second dose is given, so this is just equal to t. And let's consider the first dose. Again, it's 15 milligrams, so this is going to be plus 15 e to the power of minus 0.2. And then the time, we're told that it was given 5 hours after the first dose, the second dose, and we know that there's a 5-hour difference all the time between the two. So therefore the time of the first dose compared to the second dose is going to be t plus 5, because it's been in the bloodstream for 5 hours longer. So therefore we can work with this and then rearrange this in order to find t. First we're going to factor out 15, so it's going to be 7.5 is equal to 15 of e to the power of minus 0.2 t plus e to the power of, I'm going to expand these brackets as well, so it's going to be equal to minus 0.2 t minus 1, and then divide both sides by 15 to get half is equal to e to the power of minus 0.2 t plus e to the power of minus 0.2 t minus 1. Now, this is quite difficult to do anything with, but we notice that we have an e to the power of minus 0.2 t in both the terms. The only difference is we have this minus 1 at the end. But due to the law of indices, we can get rid of this by saying, so it's half is equal to e to the power of minus 0.2 t plus e to the power of minus 0.2 t, and then we can times e to the power of minus 1. Because remember how powers work. If we times these two together, the powers are going to add together to give this. So we can separate this into here. And now we can factorize this by doing half, and we can factor out e to the power of minus 0.2 t from both of the two terms. So it's going to be e to the power of minus 0.2 t. The first term, when you factor out e to the power of minus 0.2 t, it's just going to be 1. And then the second term, it's just going to be plus e to the power of minus 1. So therefore, from this, we can divide both sides by 1 plus e to the power of minus 1 to get that 1 over 2 to the 1 plus e to the power of minus 1 is equal to e to the power of minus 0.2 t. And now what we can do from here is take natural logs of both sides. So this would be the natural log of 2, 1 plus e to the minus 1 under 1, and this is equal to the natural log of e to the power of minus 0.2 t, which will just be equal to minus 0.2 t. Divide both sides by minus 0.2 to get minus 5 of the natural log of 2 of 1 plus e to the minus 1 under 1, and this is equal to t. Now we need to get it in this form here, and at the moment we're nowhere close to this, but one very key thing we can do is we have this minus coefficient which we can bring into the bracket in order to do 5 of natural log of 2 of 1 plus e to the power of minus 1 under 1 to the power of minus 1 is equal to t, and this will flip this fraction here, so we get the 5 natural log of 2 to the 1 plus e to the power of minus 1 is equal to t, and then we can expand the brackets to do 5 of the natural log of 2 plus 2 to the power 2e to the power of minus 1, which we can write as 2 over e, and this is equal to t. And this is the final answer, where we've got it in this form, where a is equal to 5 and b is equal to 2.